Hi everyone, my name is Raquel Ortazo. I'm the Chief Scientist of Qualitative, as well as a professor at the University of Toronto. In the previous version of this workshop, over the last few years, my talks describe our advances in building the next generation software stack necessary to solve self-driving at scale. Today, I'm going to do something different. I want you to close your eyes and fast forward into the future, where self-driving cars are going to be everywhere. While a world densely populated with self-driving vehicles, SDVs, might seem futuristic, these vehicles will soon be the norm. They will provide safer, cheaper, and less congested transportation for everyone everywhere. Furthermore, with several SDVs in the same area, we will be able to see the scene from multiple viewpoints, which may allow us to drive safely. For example, imagine the SDV driving along, and a child chasing after a soccer ball jumps into the street from behind a parked car. This situation is very difficult for both SDVs as well as human drivers, which need to correctly perceive and react to in the fraction of a second left before a potential collision. However, if we equip SDVs with the ability to transmit information and utilize the information received from nearby vehicles to better perceive the world, we could see the occluded child earlier, allowing for a safer and more comfortable avoidance maneuver. B2B communication can help not only the previous scenario, but other situations as well. With B2B, SDVs can see through occlusions, which allows for preventing heartbreaks, see at longer range, which will allow for higher speeds, and see more evidence about the scene, which allows them to take more confident decisions. One might think this additional information will actually cause a bottleneck due to limited compute hardware on SDVs, but actually, B2B allows shared and distributed computation, since every car in the network can help with joint computation. There are three important questions that we need to consider when designing a B2B system. What kind of information should we transmit? What's the best way to combine the information? And how can we minimize transmission bandwidth to communicate efficiently? For the remaining of this session, we will discuss and answer these three questions. There are three important, let's first look at what kind of information to transmit. Two options immediately come to mind: transmitting input sensor information and transmitting perception and prediction outputs. Both transmission approaches have been proposed previously, and while both improve perception, there may be better representations to consider. Let's look at each option in more details. When we transmit sensor data, we gain the benefits of no information loss. Each SDV has access to the same information seen by other vehicles. If the transmission data is later, it is easy to combine this information in 3D by, for example, just aggregating the point clouds. This is the approach proposed by Cooper, a B2B sensor fusion method. However, there are several disadvantages. Sensor data is large in size, and the more sensors there are on the vehicle, the more information there is to be sent, making this approach not scalable. In addition, aggregating the LiDAR point clouds into the shared 3D space loses important information about which SDV viewed that observation, which can provide insights into the confidence of the sensor reading on that particular area. This illustration shows an overlay of simply combining the point clouds. Our second option is to transmit the outputs of perception and prediction. The main advantage is that messages will be very compact, as describing bounding boxes and trajectories require very few parameters compared to LiDAR inputs. However, only transmitting outputs completely discards any scene context. Furthermore, output parameterizations have limited expressiveness, with rectangular bounding boxes and a fixed number of waypoints. Finally, taking outputs from all vehicles is prone to having false positives. An implementation of this idea is what we call output fusion. We simply overlay the different bounding boxes and trajectories into the shared coordinate space, as shown on the right in BEV. Then one can filter out overlapping instances using NMS or perform more enhanced fusion through filter-based estimation. An alternative is to transmit intermediate representations of the neural network used when performing joint perception and prediction. This gives us the best trade-off, as the intermediate representations are typically compact while still containing information about the scene context. Furthermore, their expressiveness is not limited, as in the case of output representations, and information regarding viewpoint is not discarded, as is the case in input fusion. Finally, using intermediate features leverages distributed computation from multiple vehicles, as every vehicle first computes them from their own sensor readings. But how do we aggregate these intermediate representations? We propose V2VNet, the first sophisticated AI-based V2V approach, which aggregates intermediate features with a graph neural network. First, sensory inputs are encoded into a compact intermediate representation, which is then compressed and broadcast to other vehicles. Then, messages from other vehicles are received and decompressed, and all features are aggregated with a specially aware GNN. Finally, the aggregated features are processed to generate perception and prediction outputs. Let's now look at V2VNet in more detail. To start, each vehicle receives intermediate features in bird's eye view, along with the timestamp of the messages and the relative poses of the senders with the broadcast range. Next, we concatenate the time delay to the message features and use a CNN to learn to compensate for messages with a delay timestamp. Note that the time delay is easily accessible, as all vehicles have access to a global clock. After time delay compensation, the messages are aggregated by another neural network. At each message passing stage, the feature maps are warped into the same coordinate frame, and features inside the region of interest are used for accumulation. This method allows us to intelligently aggregate intermediate representations in a spatially aware manner. We have discussed the different ways to incorporate information from other vehicles, but we also need to make sure the information can be sent with existing hardware quickly and efficiently. We want messages to be small, but capture the relevant information. For each fusion method, we now consider what compression may need to be done for effective V2V. For later fusion, since later point clouds are quite large, we use a state-of-the-art point cloud compression system called Draco. For output fusion, the bounding boxes and trajectories are already very compact, so no compression is needed. For the intermediate spatial features from the neural net, we can leverage existing literature for learnable image compression and adapt Ballet's entropy coding to our setting. When it comes to evaluating V2V methods, there is a lack of suitable real-world datasets. Existing datasets are created in a platoon or convoy setting, where cars closely follow one another, as can be seen on the right. Observations captured in this setting are highly correlated and therefore fail to capture the diverse V2V scenarios that occur in practice. As an example, in the convoy setting, we will never see SDVs approaching from the opposite direction. To address the lack of benchmarks, we created V2VSim, a large-scale V2V dataset using our new high-fidelity LiDAR simulator, which faithfully replicates real-world LiDAR scans. In this dataset, we take the 3D reconstruction of logs of real-world LiDAR sweeps and simulate them from the viewpoints of other vehicles in the scene. Then, all other vehicles can act as SDVs. By doing so, our SDV topologies directly correspond to real-world traffic scenarios. Our dataset contains 46,000 training frames and 4,400 validation frames, and we allow up to 7 SDVs in each frame. To create the V2VSim dataset, we leverage millions of miles collected by our SDV fleet to create simulation worlds that are realistic, such as the background meshes and dynamic objects seen on the right. Since we are doing V2V, we will be simulating sensor data from new viewpoints, which means it's important we have good coverage of the background meshes and dynamic objects we create. Here we show the process of creating background meshes with good coverage. We record real LiDAR data by driving in an area and remove moving objects. We aggregate and align the LiDAR, combine across multiple trajectories, and create a mesh surface representation. A similar process is done to generate dynamic objects. We utilize a symmetric prior to get a complete shape of the objects. Leveraging real data allows us to inject the diversity of objects seen in the real world into LiDARSim. From left to right, we can see cars with open hood or trunk, bicycles on top of the car, flatbed trunks with construction cones, and trailers with extended cars. Making sure we can detect these rarer objects as vehicles is important, as by leveraging real data, we can simulate more situations that are in the long tail. You often don't see this diversity from other 3D asset or car model databases that are created typically by other artists. Once we generate our assets, we can place them in a scene configuration, just like in a video game. We now have scalable and diverse scenes. We then perform realistic sensor simulation with physics and machine learning. LiDAR generates point clouds by shooting light into the scene and measuring travel time to determine an obvious distance. To mimic this process, we recast our scene and generate a simulated point cloud. However, recasting generally generates more returns than real LiDAR, since the return light does not always meet the detection threshold. We call this phenomenon rate-up. Rate-up is complicated to simulate by physics alone, because we don't know the physical parameters of our real world. Fortunately, using a rate-up network, we leverage real-world data and ML to bridge the sim-to-real gap. To generate the B2B sim dataset, we recreate real-world traffic snippets in the virtual world using ground truth bounding box tracks, as shown in the 3D scene on the left. With this constructed virtual world, we can now simulate realistic LiDAR from different vehicle viewpoints, as shown on the right. Each color autonomous vehicle has a corresponding color LiDAR point cloud generated. We evaluate our method and other baselines on B2B sim. Here, average precision measures detection performance, L2 error measures error of predicted trajectories, and TCR measures the collision rate of predicted trajectories. With B2BNet, we are able to reduce error in perception rate by 68% when compared to single vehicle performance shown in the first row. Furthermore, B2BNet achieves superior performance to other fusion baselines as well. By incorporating valet compression, B2BNet is able to achieve the best trade-off between message size shown on the x-axis and performance shown on the y-axis. Also, at 10 Hz, our method only requires 0.2 megabytes per second during communication, which is easily satisfied as even the cheapest dedicated short-range communication hardware provides more than 3 megabytes per second. B2B performance in perception and prediction tasks also increases with the number of vehicles in the network. As the density of SDVs increases in the real world, B2B communication will become even more effective. Notice of the nice, almost linear growth with number of vehicles. B2B provides dramatic improvements on far away and occluded vehicles, as there is a significant lack of LiDAR evidence in these cases. Furthermore, B2BNet is particularly effective at detecting vehicles with high speed, beating LiDAR and output fusion by a large margin, as can be seen on the top left. High-speed vehicles are often difficult to handle due to motion blur and rolling shutter. These effects are due to the fact that, since the vehicles are moving, the LiDAR observations become warped, like the camera image on the right, making it difficult to predict where the object is at any point in time. The previous experiments assume perfect localization of the SDV, as we need the relative poses to transform of the SDVs, as we need the relative poses to transform messages into a shared coordinate system. But in the real world, there may be localization errors. We evaluate the performance when we add noise to the estimated position and heading of our SDV. Unlike other fusion methods, B2BNet is more robust to localization errors, as leveraging a GNN allows to intelligently aggregate the messages and be more robust to this type of error. Furthermore, in the real world, we cannot always expect messages to arrive with perfect timestamps. It's important that B2B communication is robust to delay messages. Here, our proposed B2BNet is much more robust than the other fusion alternatives. In this evaluation, we account for time delay in output fusion by extrapolating vehicle trajectories, and no compensation is done for LiDAR fusion, as extrapolating LiDAR point clouds is non-trivial. We now show some qualitative examples. The ground truth is in red, B2B outputs are depicted in green, and single vehicle outputs are in blue. Here, B2BNet can detect the highest speed vehicle behind, and thus wait before performing a lane change. Here is another example where we showcase the significantly higher recall of B2BNet. This can be seen by looking at all the green boxes where B2BNet is able to detect vehicles that are missed in the single vehicle case. We now showcase B2B net results. The upper part shows the location of the self-driving cars depicted in yellow. Cyan rectangles are regular vehicles, and the green dashed circle represents the broadcast range for the Ego car. The lower panel shows P&P outputs, where ground truth is in red and B2B net is in green dashed line. By leveraging B2B communication, our detection and prediction performance improves significantly, especially on heavy occluded and faraway vehicles. In conclusion for this part of the talk, we find that B2B can significantly improve perception and prediction performance of self-driving and propose B2B net, where each vehicle transmits compressed intermediate representations and fuses messages from different vehicles with a GNN. Our method significantly outperforms other B2B methods and is much more robust to noise. There is little question that self-driving vehicles are going to be central in our society in the future, with all the advancements and discoveries that are being made. As previously discussed, these vehicles require high-definition maps of the regions that they are expected to drive in, and these maps require periodic updates. This motivates the need for a system that is able to autonomously map a region and coordinate an increasingly large fleet of vehicles in an efficient, scalable, and adaptable manner. The idea of an agent or fleet coordination system is not a new one. A similar idea has been explored in the case of the traveling salesman's problem. In this problem, we have a series of points on a plane. The idea is for the agent or salesman to visit all of the points exactly once in the most efficient manner possible, and then return to their original starting position. The vehicle routing problem is a natural extension to this with multiple agents. Given a set number of agents, which all start from the same initial starting city, all are expected to visit some subset of points so that after all agents have finished, every point has been visited exactly once. Bringing this back to mapping, each node could be a representation of cities that need to be visited, or even individual streets within a city. There has been a considerable amount of work into TSP or VRP iterative solvers, which can relatively consistently determine the optimal solution to a given problem, as seen in the case of Concord or LKH3. In the deep learning field, a few steps have been made towards developing a deep learning solver that can be considered more adaptable than iterative solvers, such as the attention module or AM, and encode, attend, and navigate or EAM. There has also been some work into exploration-based architectures, as seen in the work on value iteration networks. However, these kind of solutions each run into their own set of issues when running in a more realistic setting. When we consider real road graphs, it becomes evident that they can't just be represented by 2D coordinates on a plane, and the complex connections can only really be represented using sparse road graphs. Deep learning solutions usually require that the nodes to be fully encoded just using the relative 2D coordinates, and therefore struggle in a graph domain. Furthermore, when we are sending out vehicles in practice, they have to contend with unknown traffic conditions, random mapping failures, and other changes in the environment. Iterative solvers tend to be too slow to adapt the trajectories of an entire fleet online with all these changes, and also struggle to effectively integrate stochasticity into their model. In the field of real-time adaptation, learned differentiable communication has recently provided a means to generate deep learning models that can communicate information between different deep learning agents in a swarm. Similarly, novel methods for properly encoding a graph environment have been developed that could allow us to operate on a street graph directly. However, in practice, mapping tasks tend to be conducted in a somewhat inefficient manner. What tends to happen is an initial trajectory is calculated using an iterative solver offline, and the fleet of vehicles is sent out to perform the mapping task, as is seen in mapping attempt 1. After they return, we determine which streets had mapping failures, and we send out the vehicles again. as seen in mapping attempts 2 and 3. This process is repeated until every street has been completely mapped, which, as you can see, isn't necessarily the most efficient practice due to the lack of real-time responsiveness and the fact that you have to go back to base and then observe what you have done and then go back into the field. As a result, we approach this problem with the following proposed architecture. We extract node information from the map graph, encoding that information, and then send this node encodings to our novel conceptualization of a value iteration module. This module iteratively exchanges information between each of the nodes and allows for complex planning to occur in a distributed manner. Finally, the communication module exchanges node information between each of the agents and allows relevant discoveries made by each agent to be shared. This final output is also returned to the map graph in the form of a per node value function. Getting into the specifics of our method, our value iteration module takes in as input both the encoded node features, the adjacency matrix represented as a dense normalized distance matrix, which can be found, for example, using the Freud-Warshall algorithm. And at each node, information vectors for every other node are combined using an attention mechanism, and then passed through an LSTM module, which acts as the memory unit for each node, and has produced a new set of node features. These are added to the original features as a residual, and this process is repeated over several iterations. At the very last iteration, we decode the node features into a value function at each node. After masking out the nodes that have already been completely mapped, we convert our value function into a probability distribution of traveling to that node in the next step.
Here, we visualize the multi-agent routing value iteration network's internal action value function as an ever-evolving heat map. On the left, you can see agent 1, and on the right, you can see agent 2. The yellow and green clouds represent the heat map values and therefore which region the agent is most likely to visit in its next step. The red and blue dots represent the vehicle's positions when making these decisions. The agents generally alternate between focusing on specific regions to systematically map and more generally exploring new untouched areas.
In order for information to be exchanged between agents, and in order for information to be retained from previous steps, we integrate a communication module into the system. We decode the final node encoding into a communication vector of node features. These features are saved by each agent into a memory unit. When an agent takes their next step, they use yet another attention mechanism to combine information from the other agents into a single set of node features. This process can be interpreted as determining what information is most relevant and accumulating that information. Now we will illustrate how we construct our proposed mapping simulator benchmark and how we generate our novel strongly connected map graph dataset. We begin with taking the map graph of 15 international cities and converting them to weighted adjacency matrices. The nodes represent the streets that need to be visited, and the weights of the edges represent the expected time required to travel from one road to a different adjacency road. Next, we randomly sample these graphs for strongly connected smaller subgraphs between 10 to 25 nodes in size. We were able to generate over 23,000 graphs through this practice. Instead of relying on the two-dimensional coordinates as is done in the traveling salesman problem or the vehicle routing problem, we make no such assumption and instead only provide our model with a weighted adjacency matrix. Once we have all the sample subgraphs, we then stochastically add realistic challenges. First, we simulate what the realistic traffic should naturally look like, and then use the simulators to assign each street in the graph a congestion value. As this value increases, the time required for a vehicle to traverse a street shall also increase. This congestion value is initially unknown to all vehicles, and only becomes known after a vehicle has visited this street, thereby mimicking unknown traffic conditions. We similarly simulate the possibility of there being mapping failures when each vehicle attempts to visit a street. This could be caused by unforeseen occlusions, hardware malfunctions, or other unpredictable issues. The way we simulate this is by assigning each street a difficulty index. This index is uniformly sampled from 1 to 3 and represents how many passes are required before the mapping task can be considered complete. As this index is unknown to all the vehicles, this is tantamount to each street having a random probability of needing to be revisited. We tested our model using two main learning techniques. The first that we discuss is imitation learning. In order to find a ground truth basis, we first transform the street graph by duplicating nodes according to how many passes will be required before the mapping task is complete, and alter the edge weighting to reflect the unknown traffic conditions. This allows us to use traditional VRP solvers to find the optimal traversal path, since we no longer have a non-stochastic states in our graph that will require online updates. In our case, we use solutions provided to us by the LKH3 iterative solver as our ground truth, and train using teaching forcing, where the agent unrolls according to the ground truth path. We also train using reinforcement learning in order to verify the generalization or generalizability of our method. We set the negative total traversal cost to be our reward function, and use episodic rewards. Using episodic rewards, we train using vanilla policy gradient. We now present the primary findings of our study in the form of the average cost of a traversal. It should be noted that for all deep learning models, we train only using graphs with 25 or fewer nodes, and only with 2 agents at a time. Cost in this context represents total traversal cost. And gap represents the percentage gap between this method and the Oracle ground truth optima. And runtime is simply the runtime of the algorithm in milliseconds. Firstly, we find that our model generally is able to outperform the solutions provided by the state-of-the-art, represented by AKH3, and also outperforms a naive greedy search by a considerable amount when enrolled with a single agent. Scaling now to 5 agents on graphs with 4 times as many nodes, we see a similar trend, where our model outperforms the state-of-the-art solvers and is able to get the closest performance to the true optimal out of the basic alternatives. Compared to other deep learning architectures, this pattern is repeated. We show that our particular architecture, when compared to other generic graph-based alternatives such as GAT or GVIM, results in the best performance in the single agent case. When it comes to the other deep learning TSP solvers, we found that the reliance on the 2D coordinates and the inability to adapt their traversal hampers their performance in general. Qualitatively, we also observed that they ran into significant issues when attempting to deal with the multiple traversal aspects of our simulated benchmark, and as such, failed to produce adequate traversals. Due to the inability to adapt and communicate, we only consider them in the single agent setting. Finally, the trend is maintained even when again scaling to larger graphs and increased number of agents. In order to reach a fair comparison, we equip each of the alternative deep learning models, seen here, with our communication model, and therefore only evaluate the path planning abilities of the internal architecture. We would like to note how our method, when trained with imitation learning, scales much better relative to the number of nodes than when trained with reinforcement learning. Here, we qualitatively compare the mapping process of our method to that of another competitor architecture, specifically that of a generalized value iteration network. We find that our model results in a more thorough mapping process, where we prioritize filling in all regions completely over exploration. The competitive network seems to prioritize exploration over completeness, and as such, it takes noticeably longer to complete the mapping task. Due to the mapping failures that can occur and the lack of information about where these failures are a priori, ensuring completeness of a given region becomes a non-trivial task in itself. We similarly compare the qualitative performance of agents trained with reinforcement learning to agents trained with imitation learning. When scaling two much larger graphs, we find that imitation learning agents are able to prioritize exploration while simultaneously ensuring that revisiting previously visited regions is done in an efficient manner. One question that we sought to tackle in this work was to determine how adding more agents affect the performance of the model. Here we can see that as we add more agents, the total cost of performing the mapping task only marginally increases, meaning that the mean cost per agent decreases nicely with the number of agents used. Next, we sought to evaluate the generalizability of our approach. We did this by first changing how the mapping failure distribution was represented, and found that regardless of the distribution, as long as there was a decent degree of stochasticity, our model outperformed current state-of-the-art best practices, again represented as LKH3. It should be noted that all evaluations were performed on the same model trained over a uniform 1-3 distribution. We then verify a few more things about our model. Firstly, we determine that agents trained with reinforcement learning scale slightly better to the number of agents than agents trained with imitation learning. We also determine that the runtime of our algorithm scales much better than current state-of-the-art. This suggests that we could feasibly run our algorithm online. We also finally determined that increasing the number of iterations in the value iteration module, even after training, can provide some increase in performance. We believe that this can be attributed to stored information in the latent features of the node encodings. In this section of the talk, I show you a novel approach to perform online routing of a swarm of agents in the realistic domain where dynamic challenges are present. By making use of learned value iteration transitions and an attention-based communication protocol, our model is able to outperform the state-of-the-art on real street graphs. Furthermore, it is able to do so in a scalable manner. Note that our novel attention-based graph encoder and a scalable communication method can be directly applied in fields from ride-sharing to drone fleet management, and as such, has the potential to be extended to far more applications in the future. Here is a final visualization of our multi-agent value iteration model at work.
This work will be visualized on 2,426 streets in Chicago with a fleet of 20 agents. On the left, you see the lasting vehicle trails as they traverse the city, and on the right, their immediate positions. The bright dots at the top of the screen represent the ending and starting locations of the vehicles.
To conclude, today we fast forward into a future where self-driving vehicles are everywhere. We saw how vehicle-to-vehicle communication can be utilized to improve significantly the performance of perception and prediction systems, particularly by seeing through occlusions and at range, resulting in potentially safer and more comfortable maneuvers. Finally, I show our approach to route a fleet of vehicles to map entire cities in a dynamic and coordinated manner. This is all for me today. Thanks for your attention.